Okay, so yeah, let's continue. I think I almost finished last time work. Maybe I just started again. Okay. Okay, I think I left somewhere with the continuous part. Okay. Okay. Okay, I'll leave exercise to for the continuous part. Okay, and then okay. So now let's continue. So yeah. So last time I said that we derived a continuous back junction between this gamma. Really it's like yeah gamma take away x to the which is x to the quotient by the relation gamma to this x. So yeah, so then the statement is okay. So then the inverse mapping from x to gamma take away sorry x to the is also continuous because gamma is a selective open map. Okay. Is also continuous because this gamma is a surjective open mapping. Open mapping. Okay, so we know that this gamma is surjective by the property of the Fourier projection. So why is it an open mapping? Oh, okay. So why is the open mapping? Okay, so we know that this is the universal covering space of a connected, locally simply connected, locally contact household space X. Okay. So if I take a point here, wait, okay, so if I take open set, I want to show that this is open. So okay, so
point on U, basically I can pick so for each point of U, I can pick, let's say, for any, let's say, P tilde. Okay. So we basically, the idea is that we can pick U tilde P, right? Because I do the projection here, and then I find an evenly covered neighborhood of this UP around this P, and then yeah, I add this U tilde P to be the one of the destroyed component of this gamma inverse of UP, right? So and then so this is open, and then yeah, so then I know, because this is open, right? So then you just replace this by this U tilde intersect this U tilde P if necessary. So then we get yeah, just replace that, okay. And then so then this is the neighborhood that contain EU, right? So why is it open mapping? Because okay, basically I want to show that this okay, our goal is to show that show this U, which is equal to gamma of U tilde is open. Okay. So why it is open? Okay. Why it's open? Because okay. I think the reason is that I want to say that it's a union of okay. I think it's true, right? Because wait. Okay, so because for each point P, yeah, you can find such neighborhood that, wait, okay, so why is it true? Okay, so that P is this U, right? And then you take the and then you have you take the pre-image yeah, you take a pre-image, okay, under this U tilde, and then what you do is that okay. Yeah, so then what you do is that you so you first you pick the you pick the UP, right? Yeah. Yeah. So now for this p tilde, you do the operation here, right? This p tilde in u tilde, then you can pick. So first you pick even covered set up, okay. Okay, and then you do the projection back, okay. Now you get a such that, sorry, p is in this, yeah. And then you replace the p by this one, okay. And then, okay, and then because, okay, so since you have this gamma of u tilde is equal to u, then you have that, and gamma of, and then this u p is contained in this u, right? So this implies that, yeah, okay. Let's see. So I want to say that this gamma of up is claim gamma ut is contained in u. Okay, why? Because each x is in that. Okay. Yeah. X equal to gamma of some, let's say x tilde, right? Or x prime, x tilde, where x tilde is up, and then since x tilde is also in, up is contained in u tilde, so therefore x tilde is also contained in u tilde, and then, yeah, this is contained in, okay. Yeah, so this is true, okay. And then, let me think. Yeah, I think that gives the result, right? So, where am I? Claim that. Okay, so where am I? Oh, yeah. So, yeah. Wait. Okay, I want to show that this is evenly covered set. Oh, okay, yeah, because this gamma is a local homomorphism, is a local homomorphism, right? So yeah, so yes, so yeah, because this gamma is a local homomorphism from this original cover, like from this u to the p. This u to the p is like the original, like this gamma, because this gamma retreated on this u to the p is a homomorphism. So therefore, when you take an intersection, it's also open. Okay. So therefore, this is open. Okay. And then we're done, right? We're done. So because yeah, for each point we can find such neighborhood, right? So yeah, so therefore U is a union of open. Yeah. Okay. Okay. Yeah, I think this is the open mapping, and then the inverse mapping is also continuous. Let's see why the inverse mapping is also continuous. So I know that the inverse mapping from okay, so let's see what is the map. So okay, I know that this is like the equivalent relation, right? So basically this is like the equivalent relation of this like equivalent class of points in this like current universal coordinate space that's related by x equal to y if only um, y is equal to the image of x for some x. Like yeah, y is equal to some gamma of x for some yeah some whatever some little r. I use the letter little r. So equal to little r like some r of x where r is belongs to the where r belongs to the deck transformation. Okay. Yeah, sorry. Where r belongs to the deck transformation group or something. Yeah. So let's call it the deck transformation group. Yeah. So yeah. So this is that. Okay. So what do you mean by inverse mapping? So okay, so what is the forward mapping? So the forward mapping is so gamma. So this is simply just under this gamma. I use the letter gamma to denote that it's equivalence cap model quotient by this relation. Okay. And then this goes to maybe I use letter x to that. And then it goes to let's see if it goes to gamma x, right? So we showed last time. Yeah, I think we showed last time, yes. Okay, so now, so suppose that we have the, okay, we showed that last time that it's a bijection, right? So we showed last time it's a bijection. So now, the inverse mapping should be just given by this x goes to this equivalent class, right? Where, yeah. It's either fiber. Okay. Okay. So now let's see. Okay. So now what do we do? Let me see. So now, okay, so now, okay, yeah, we need to show that this is actually a continuous map, right? Okay, so our goal is to show that this is continuous, okay? Show, so let's, yeah, so let's give a name for this one. So, define it as 5, okay. Or like P or something. Yeah, so what's the letter? Let's say, yeah, let's just use 5. Okay. Yeah, so show 5 from maybe I use 5 inverse. Okay, I think it's better. Okay. No, I don't think 5 inverse is good because if you take the inverse, to write inverse twice, so maybe I just use phi. Okay, so basically, let's see. So basically that so that U to be X open, and then we take the phi inverse of U. Okay, so let's see why this phi inverse U is open. So because so this is what? So this is essentially the the universal covering space that's being quoted by this. So that's exactly the universal covering space that's quotient by the equivalent relation of this gamma of this related by this declination mapping, essentially, right? Yeah. So roughly speaking, okay. Then so I think the idea is that if you take the inverse, if you take the phi inverse of U, then what you should get is that okay. I think the idea is that if you take gamma inverse of U, right? You take gamma inverse of U. So because this gamma is a continuous bidirectional, right? So if you take gamma inverse, it's open, right? So and then this is the open set, okay. So then if you so this is open in this X2 then, okay. So then this is open in this universal covering space, right? And then if you so what do I want to say? Okay, I want to say that if you mod out this with this one by the equivalence relation, right? Okay. So so I use letter P to denote the projection from this universal cover to the quotient space. Okay. So so that P is from this to the quotient space. Okay. And then so we have that this this what because okay, so now we have this set is open, but wait, okay. Oh, okay. I see. Okay. I think it goes. I think it goes in like in the way that if you take any open set, right? If you take I want to show that basically the phi inverse of this open set is open in the quotient space, right? So then what does that set equal to, right? If for the quotient space. Or why this phi inverse is open, right? Why this so why this phi inverse of U is open in gamma taken away X2, right? So why is it open? Because okay, I want to say that because if you take the projection inverse of this map, right? Because because it goes and then I think that's okay. I want to show that. Okay. So let's say claim. So we claim that we take the projection inverse of this map. I think it should be open to this gamma inverse of U, right? so here you take any x. And then what you have is that, okay. So this implies what? So this implies that x is equal to, okay, p of some x tilde, right? Where x tilde is in phi inverse of u. So then this implies that x tilde is equal to phi of hold on. The p inverse. Okay, I think I messed up. Yeah, I think I messed up with the sign with some with some notation here. So so let's say what this okay, so this x. So this x should be like x tilde, right? Because it's in the covering space, right? Yeah, and then okay, so and then is equal to p of, okay, so wait. What do you want to say? Is equal to p of what? P. Oh, okay, okay. No, sorry, I completely messed up. Let me check. X is in P inverse. So what does P inverse mean? P inverse means that okay, P of X is equal to that. Shoot, okay. Okay, sorry. So this implies what? So this implies that what does that mean? P of x, T of x is in phi inverse u. So what does it mean? Oh, okay. So yeah, so phi of u of x tilde is u, right? Okay. Okay, so okay, so okay. So now what? Okay, so I want to show that this x is in. I want to show that this guy is in gamma inverse u, right? So y is in gamma inverse of u. So y is in gamma inverse of u. Okay, so I know that this p of this x tilde is what? Okay, so if you have a x tilde here, the p is like you map it to the equivalence relation, right? And then phi is okay, and then for the phi, right? Okay, I think it's just very directly, right? Because this phi basically just like the Yeah. So now for the phi, you map it into the gamma x, right? So basically, yeah. So basically, so this implies that. Yeah. Yeah. So, wait. Yeah. So that implies that. Um, I think. Yeah. Okay. 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 So now let's do the. Yeah. So let's do the reverse direction. So if you pick any extruder in this gamma inverse of u, right? So then what is the so why is it that? So so this phi inverse of u basically is you go to the equivalent relation, right? So hold on one second. Okay, what is phi inverse u? Phi inverse u is okay. Set okay. Okay, so this implies that gamma x is in u, right? And then
okay.
oh sorry, yeah. Gamma x is in u, and then okay, and then this implies what? This implies that gamma x is in u. Okay. Yeah, I think it's very direct, right? Because so this implies that the inverse of this x, which is the same thing as yeah, same thing as this guy, okay, and then wait. Yeah, so this is the phi inverse x, okay, this is phi inverse of x, and then okay, so I want to show that this so why this x tutor is gamma inverse of u. So let's go in this way. Okay. So so now we have okay, so yeah. So let me show that this P of this x tutor is right? And then what is this P of x tutor? So P of x tutor is equal to yeah. And then what is that? Okay. Okay, now since okay, so since this gamma of x tutor is x is into u, therefore we have yes, okay. Which is with x. Yeah, okay. Yeah, so that's the proof. Okay. Okay. So now yeah. So now let me think. Oh yeah. So yeah. Oh yeah. So this is true, right? So this is true. Okay. So then we know that oh yeah. So yeah, I think the result's false. Yeah. Okay, the result's false. Okay. So okay. So yeah. So this is a continuous mapping. And then, okay, so let me continue. So, okay, so lemma, okay, so lemma 10.2.4 implies that gamma of gamma is a common map. Okay. Lemma 10.2.4 implies that. Okay. I will remind you of what this gamma is later. Implies that okay, this gamma of gamma is a covering map. Okay, so okay, let me remind of myself what is this lemma 10.2.4. Okay, so lemma 10.2.4 is yeah. So remember we have talked about the topological lifting theorem, such that you have the so you have the space. So yeah, so you have the space. You have a space like this x, and then you have like this y. So they are all connected. Okay, and then this y hat is a covering space. Okay, and then this is a continuous mapping, and then this phi is continuous mapping, and then this phi hat is a lifting of this phi. Okay. And then yeah, so this lemma basically says if there is another lifting, let's say phi hat prime, such that this phi such that it agrees with this phi hat at some point, then they're the same. Okay, so this is one part. Another part is that if this phi is a local homomorphism, then the phi hat is also a local homomorphism. And then third part is that if this phi is a covariant map, and then Y is locally connected, and then this phi hat is also a covariant map. Okay, so this is the lemma 10.2.4. Okay, so what is gamma of gamma? So so this gamma of gamma is actually so this gamma of gamma is actually the quotient map. So wait. So this gamma of gamma is this quotient map. Okay, sorry. Yeah, so this is actually the quotient map. Okay. Okay. So okay. So Y is a covariant map. Let's see. Y is a covariant map. Wait, do we? Oh, yeah. Okay. Okay. Covering map. Yeah. Let's try this. Okay. So yeah. So wait. Wait, did we show that this map is a it's a projection? It's a covering projection. Did we show that? Oh, okay. So, okay, yeah. So, yeah, I think the idea is that because here we have this gamma take away this x tilde, right? And then we have that, yeah, so this is like this is what? It's a continuous projection, right? Yeah, so, okay, continuous projection means that, wait, so, it is an open mapping also. Oh, okay, yeah. So we just showed that the inverse mapping is also continuous. Okay. So that gives you a homeomorphism. Okay. So homeomorphism, yeah, I think this just implies that it is it's a current space, right? Because
you have the map as wait.
yeah, it has surjective map, and then
You have the locally. You have this.
because it's a homomorphism, so therefore locally there's also a homomorphism, right? Yes. Okay. Yeah, and then therefore yeah, therefore this is a covering space, and then it is connected. Yeah, I think it's connected. Yeah, because it's an image of continuous map, right? And then okay, we know that this X is connected. Okay, this is by our definition or our assumption. And then this is X2 is also a universal covering. So yeah, it's also connected. So yeah, so therefore they are all connected. Okay. And then what about this map? So yeah, so this is like okay. Yeah, so this is like the
Covering projection.
and then is this X locally connected?
I think so, right? Because by our assumption, this X is locally connected, right? It is locally semi-connected. Okay.
Yeah, so it's connected, locally connected because yeah, okay, and then okay, then by the lemma 10.24, it is a covering map. Okay. Okay.
So yeah, so yeah, it's a little yeah, it's amazing. Okay. Yeah, it's a little amazing here. Okay. All right. So let's let's see what's okay.
Oh, I think that shows the result, right? Oh. Yeah, so this is a homomorphism, yeah. And then yeah, the quotient map is a covering map. Yeah, we just showed that. And then yeah, and this diagram is commutative. Wait, why is wait, sorry, why is commutative? Yeah, because it's a quotient map, right? Yeah, because yeah, because if we quotient and then we do the phi, it's the same thing as you do the gamma directly. Yeah. Okay. Okay.
Yeah, I think that's yeah. I think that's a proof. Okay. So okay. Okay, I think okay. All right, so let's